Okay, hi everyone. We are working with logs again. How to solve logs. We've worked before on how to solve a basic log, and we did it a couple different times. Let's give you an example. If I write log base 3 of x is equal to 2, we have two ways of solving it. We can do the identity method. And we say circle of logs, 3 squared is equal to x. So 3 squared is equal to x. That's one way of doing it. And this is pretty easy. X is just equal to 9. Or we could use exponents on both sides. This is more like the algebraic approach. So if I use 3 to both sides, the log and the exponent cancel out, the base cancel out, leaving me just x equals to 3 squared. Right? Very similar, but one uses algebra, the other one just uses a straight identity. Now for us today, what if it's not a nice single log? What if I give you a problem that's a mix of multiple logs on the same problem? What if I write log of x plus log of 2 equals to 2? Sorry, log of 2 equals to 2. Now, in this problem, it's not very obvious necessarily what this would be. Like, can you think of a number here that when I add a log plus a log gives you 2? Remember, a log of 2 is a decimal number. Okay, log of 2 is a decimal number. So here's what we're going to do. We're going to use our rules about adding, subtracting, multiplying logs. What happens when we're doing these operations to logs? To write them as one log, to combine them, so they can form Captain Planet. So when we're adding logs, we are multiplying them on the inside. Hopefully remember this is really x times 2 equals to 2. Or you can write it as log of 2x. That looks a little nicer, right? 2 times x is 2x. Now, since we have now one log, we can then solve it any way we want. We can rewrite this as our identity, knowing that this is a common log of base 10. 10 squared is equal to 2x. Circle of logs, 10 squared is equal to 2x. Or we can do the base to both sides. We can make them both exponents. Remember, logs solve for exponents. So this guy is an exponent already. So I'm going to make 10 the base for that exponent. The log and the base 10 cancel out, leaving me 2x equals to 10 squared. As you can see, very similar results. Left side just the algebraic way to show how we do it. The right side is just a straight identity. So 2x is equal to 100. X is equal to 50. Now, I would never have guessed that log of 50 plus log of 2 is equal to 2. No way would I have ever guessed that. Just to verify that on my calculator, let's see if I can find my calculator. No ads, no ads. Okay, so if I wrote 50 log plus 2 log, and that gives us that 2 number that we were hoping for. Okay, so not really a guess and check type problem in this case. So let's look at another problem here. If I write log sorry, that looks terrible. Log, let's do 49 x minus log 49 5 is equal to 1/2. Now this question is a little more tricky, but does it change the step that we were doing before? How do we combine these logs on the left hand side, log and log? They're subtracting each other, so let's see. Do you remember what happens if I'm subtracting on the outside? I'm doing what on the inside? If I'm subtracting on the outside, what am I doing on the inside? If I'm subtracting on the outside, I am logs base 49 dividing on the inside. Okay, now that we have this point, we can again solve this in two different ways. We can have these identity 49 to the 1/2 power is equal to x over 5. Or on the left hand side, we can just take the base 45 to 49 to both sides. X over 5 is equal to 49 to the 1/2 power. And both of these ways are totally okay. I would label this as identity on my work. This is important that you label it so the reader knows how you got there. Now, to solve this problem, you have to know that the 1/2 exponent is really a radical. This is really the square root of 49. And the square root of 49 is 7. We can multiply 5 to both sides. X equals to 35. Would I have ever guessed that? Probably not, I wouldn't. Now, if I want to double check this on my calculator, this would be a long check. Log base 49 of 35 minus log base 49 of 5. This would have to equal to 1/2. Now, I'm going to check that on my calculator. If you remember to write this, we need to change a base. Log of 35 divided by log of 49 minus log of 5 over log of 49. Does this equal to 1/2 for us? Just to work it out for you, just to show you that this is possible for us to check. So 35 log divided by 49 log equals some crazy number minus, I'm gonna do a parentheses here just in case, 5 log divided by 49 log. I'm going to close up my parentheses, hit equals, and we do end up with that 1/2 that we wanted, that 0.5. So the first skill is to talk about, hey, if it's not 1 log, we can't rewrite this. So we have to write it as 1 log by combining whatever method that we know how to do. Okay. What if the logs are nice and set up for us? What if I end up with a bunch of logs here? If I say log of x plus 8 and log of 5x. Okay, let's say these are equal to each other. Now for this problem here, we could get logs on one side, or if you remember, what's the inverse of our log? In this case, if I put a 10 on both sides, remember this is a common log, these logs would actually cancel out. Another way of looking at this is, hey, aren't these both logs? So if they're both logs, shouldn't these two values be exactly the same? So shouldn't x plus 8 equal to 5x if I wanted the logs to be the same? All right, so that's one way of doing it. Again, the other way, if I write 10 to both sides, logs will cancel out, leaving me x plus 8 is equal to 5x. So both us just using some common logic here, or us using our algebraic methods, give us the same answer at the end. Let's go ahead and solve it. I'm going to move the x's over. Minus x, minus x, minus x, minus x. I'll just solve for one side here. 8 is equal to 4x. X is equal to 2. And if you let's go ahead and plug it back in. If I say log of 2 plus 8, does that equal to log of 5 times 2? Yeah, because they're both going to be 10. Now, the next follow-up question is, sure, this worked for an easy common log. Does it work for any log? Well, what if I wrote natural log? Natural log of 7x. Okay, so in this case, what is my exponent that I could use to get rid of natural log? So hopefully you remember natural log is really log base e. That's what natural log is. So if I put an e to both sides, we're left with 4x plus 12. And it equals 7x. Or if you want to use our, hey, aren't the logs equal to each other? So shouldn't the insides be equal to each other? So we could just say, hey, identity is 4x plus 12 is equal to 7x. Okay, same way. Let's go and solve for x minus 4x to both sides. Then divide by 3, x is equal to 4. And if we go ahead and try it again, natural log of 4 times 4 plus 12, or natural log of 7 times 4. This is 8 plus 12. What is that? 8 plus 12? No, 16 plus 12 is 28. And they are equal to each other. So one thing for us to get used to is that we shouldn't be scared about logs. It's just another tool. It's like a square root. It's like an exponent. Logs are just another tool that we have to learn how to deal with. And logs do come in, will be helpful to us when we do our next example, when I see you guys next class about solving for exponential growth. And that is a big deal where we use it. Okay. let's look at another problem here. If I wrote natural log of w squared is equal to natural log of 9. Well, great. We can say w squared is equal to 9, right? Because they should be the same. Or if we do the algebraic way, what's the inverse of natural log? We're going to make e to both sides, and those will simplify out. W squared equals to 9. And I think we have to know both methods. One is just logically, right? That's like SAT idea. Hey, that just has to be true. And the other way is, what method would I use to get rid of the natural logs? And that would be e to both sides. So w is equal to the square root of 9, which is 3. In this case, positive 3 for us. Or negative 3, right? Negative 3 would also work, plus and minus. Great. And that's it. Let's see.